The craft of shaping and forming metal is one of the oldest skills in the world. And long before the Industrial Revolution, it was known that many metals are easier to work when they're hot. The ring of the blacksmith's hammer was a part of rural life for centuries. An expertise handed down from father to son, from generation to generation. But today, manufacturing design teams have much more versatile and exciting techniques to play with. They can shape metal by machining, but this is expensive. It needs skilled men to do it, and not all materials can be machined easily. Metal can also be formed by casting, but you need metal which can be melted fairly easily so that it'll flow freely into the cavities of a mold. But again, there are drawbacks. Some stainless steels have a poor fluidity, and even when the metal used is fairly fluid, the finished article may not have enough tensile strength and toughness to do its job properly. Forging, on the other hand, is an excellent method of inducing both strength and toughness into metal. Here you take the hot solid metal and shape it using a large force controlled with great precision. Forging in this way develops the maximum impact strength and fatigue resistance. An important, indeed vital consideration in these days when metals are expected to perform at high speed and under great pressure. Put simply, forging is the process of forming metal into a specified shape by applying an external force. In this village forge, the heated metal is placed under a hammer, and the final shape of the forging is determined by the tools pressed onto the metal by the weight of the hammer. They're what's known as swaging tools. This is an ideal way of making small one-off articles. But what about a ship's propeller shaft, for instance? Exactly the same principles of forging apply, but on a vast scale. And the operation is a slow and delicate one. This technique is known as hot press forging. It begins with an ingot of metal, which can weigh anything up to 70 tons. The process will not only change the shape of the ingot, but also its internal formation. When working an ingot of this size, it's important to get it to the correct forging temperature steadily and slowly. Too rapid heating would cause steep temperature gradients, which could set up thermal stresses and quite possibly crack the metal. In this particular case, the ingot was preheated to 650 degrees centigrade for 12 hours, and then held at this temperature for another 8 hours. It was then raised to 1250 degrees and held there for a further 12 hours. As the temperature mounted, the metal relaxed, as it were, and the internal stresses were reduced. When the ingot has reached the correct temperature, it's moved to the forging press. The 4,000-ton press requires considerable skill, experience, and teamwork to operate. Although the job demands great precision, speed is essential. From the moment the ingot leaves the furnace, it starts to cool, and it'll only remain in a workable condition for a couple of hours. Trying to prolong this time isn't possible. Raising the temperature higher would result in oxidation and a coarse grain structure. The ingot would lose its malleability, and instead of forming under the weight of the press, it would just crumble. The forging process, as well as changing the shape of the metal, must enhance its mechanical properties. The position of the ingot in the press and the successive applications of force have to be carefully controlled to prevent what's known as forging laps, or folds in the surface of the ingot. The press operator presets the reduction, and the depth of each bite can be controlled to within 1 millimeter. Forging breaks down the original coarse grain of the ingot structure. It assists refinement of the grain, and it'll give the metal the necessary mechanical properties when the completed forging is eventually heat-treated. At this stage, the metal has been worked into 2 dimensions only. It hasn't been worked along its axis. But apart from refining the grain size, many other changes have been taking place within the metal. Internal cavities in the ingot are gradually being removed. Before they're forged, ingots tend to have a variable chemical composition, and they'll contain non-metallic substances. Forging draws out these undesirable elements along the whole axis of the ingot, imparting a fibrous structure, rather like a well-formed plank of wood. And that's not a bad analogy, because the grain in the metal is very much like a piece of wood. It's much easier to split it along its grain rather than across it. It's this fibrous structure which affects the strength of the material, and it varies from plane to plane. The purpose of forging is to impart the maximum strength to the metal. Ideally, the design engineer wants a metal grain flow which gives the greatest strength to the areas under greatest stress. This ingot has already been forged in 2 dimensions, and now it's being forged down its long axis by a process called upset forging. It's the perfect way of increasing the diameter of the metal without decreasing its strength. If you machine the metal, you'd cut into its fibrous structure and obviously weaken it. Enhancing the fibrous structure of the material in all 3 dimensions is essential if you need a component which has to withstand heavy stresses in all directions. Take a die block, for instance. This needs to be uniformly strong and tough because of the stresses under which it has to work. When you forge a die block, you work it in all 3 directions to achieve the ideal grain flow. These die blocks started life as part of a rolled steel bar called a bloom, with the grain flowing along the direction of rolling. A section, it's called a billet, is removed and heated in a furnace. The first step is to upset forge the billet and reduce its length by half. Technically, you'd call that a 2-to-1 forging reduction. By upsetting along the longitudinal axis of the bloom, the metal will be worked in a new direction and will be given the required fibrous structure. Ideally, this means changing the original grain so that it flows identically in all directions. Controlling the temperature of the metal is crucial. The lower limit of temperature at which the forging is completed is called the finishing temperature. This mustn't be too high, otherwise the final crystallization will result in grain growth and a coarse grain size. If the finishing temperature is too low, on the other hand, then the metal will be what's known as cold worked, and that can lead to distorted grains and the formation of cracks in the metal. Great skill is required to finish the work at the correct temperature. The material can be rotated about 2 axes and turned so that it's forged down each of its sides. Once the 2-to-1 reduction has been reached, then the metal can be given its correct dimensions. Forging these blocks so that each has square sides and sharp corners requires a high degree of skill. When the block is finished, it's stamped with an identification mark, a sort of craftsman's signature. It's a check system, so that if there is a failure of the component, it can be traced back to the time of forging and even the name of the man who forged it. The original direction of the grain flow, the type of steel used, the production number, all the essential information about the metal is stamped on it. From here, the block goes for its heat treatment before it's finally machined into the shape of the finished die. Die blocks are a key element in another common forging process known as drop hammer forging or stamping. One half of the die is attached to the anvil and the other to the hammer. The hammer is lifted to the appropriate height above the anvil and allowed to fall onto the metal billet. As the hammer falls, it forces the metal into a cavity between the two halves of the die. Drop forging is an ideal way of manufacturing all sorts of complicated shapes. Everything really, from small levers and gears to intricate crankshafts for diesel engines. All you do is vary the weight of the hammer and the shape of the die. This crankshaft is for a truck, and it's probably one of the most stressed parts of the engine. It starts off as a metal billet weighing about 55 pounds. Raised in the furnace to 1300 degrees centigrade, it's brought out and taken straight to the anvil. The hammer is raised to its full height and released. This is done time after time until the leader of the forging team, the stamper, is satisfied that the correct forging has been achieved. After each forging has been made, the two halves of the die are sprayed with a fine graphite oil to cool the die, reduce wear on its surface, and generally help the metal to flow more easily in the cavity. Sawdust is thrown on in between the hammer blows to help prevent the hot metal from sticking to the die. The hammers themselves are rated according to the maximum kinetic energy they release. The purpose of the first hammer blow is to remove the surface scale and round off the edges of the hot billet. The force of the hammer causes plastic flow in the metal, and this gives it a tough, fibrous structure. The dies are designed to induce the most advantageous flow of the metal, so that the grain follows the general contour of the forging. From the heavy hammer, the forging goes to a much lighter hammer. Here, the edges of the crankshaft are finished off. Then on to the final stage of the process, a hydraulic clipping press. Here, the surplus metal, it's called the flash, is removed. On the same hydraulic press, the crankshaft is straightened. This corrects any distortions which may have been caused in the forging process. One drawback is that a lot of expensive prime material, about 20% of the original forging, ends up as waste. But despite this, it's a method which produces forgings fairly cheaply and in all sorts of sizes, anything from an inch to several feet in length. And a wide range of metals can be used, almost anything from steels to alloys of titanium and aluminium. A variation of the drop hammer forge is pressure-closed die forging. Here, the metal is forged with a continuous force applied slowly, rather than repeated hammer blows. The force is much more powerful here, and can sometimes be the equivalent of 6,000 tons. It's obviously a faster process than stamping, and the high cost of the machine is justified by the increased output. Another bonus is that the dies are more easily aligned with each other. This can give a better accuracy in the dimensions, as there's no jarring of the component in the die. But the big advantage of pressing over drop forging is that the piece is worked uniformly throughout the metal, compared with drop forging, where the impact tends to be confined to the surface. This can be important when forging large components like these diesel engine crankshafts. They start life as 140-pound billets cut from a length of steel bar. Then they're heated to the forging temperature of 1260 degrees centigrade in an induction furnace. Next, they go by conveyor to a pre-forming press, which rounds off the corners to prevent excessive wear on the die blocks. From here, they go to the press itself, which is capable of applying pressures up to 6,000 tons. It's one of the largest enclosed die presses in Europe. The pre-formed billet is first of all placed on the impression mold and then onto the finisher impression. A pair of dies like this could produce up to 8,000 components before they wear out. Next, the forging goes by conveyor to a clipping press where the excess metal, the flash, is removed. The crankshaft is moved onto the hot set press to get rid of any distortion. The specification of these particular crankshafts calls for them to be hardened by oil quenching from 870 degrees centigrade and then tempered. As you can imagine, this is a hot and noisy place to work in, one where automation can make the working conditions much easier. During the last decade, special forging equipment has been designed to cope with long runs. Machines like these are capable of producing 4,000 forgings an hour. They've excited a lot of interest among designers and production engineers. This particular machine, it's a variation of the pressure-closed die technique, is producing gear blanks for the car industry. First of all, steel rod is heated to the forging temperature by passing a current of 20,000 amps, 100 volts, through it. That's enough power to heat a whole town. Then the medium carbon steel rod goes to a holding furnace to make sure that it's uniformly heated. And from there, through a set of water-cooled rollers, which keep it straight and true for the forging process. We can't show you what happens inside the press, but we can show you the progressive stages in the forming of the metal. The rod is first cut to length. Then it's passed to a pre-forming die. Then onto a molding die. There's a finishing impression, and finally a hole is punched out in the center of the gear blank. Each of these processes is carried out with one stroke of the machine. The whole cycle of cutting and forging is water-cooled. the gear blanks are taken to be heat-treated. The central cores go for scrap. Like other conventional forging processes, there is some waste material, and this has led cost-conscious designers to come up with a bright idea where there's virtually no waste at all. It's called powder forging, and it's based on the principles of powder metallurgy. A steel powder preform of accurate weight and shape is prepared, and from this the finished part can be produced with much greater accuracy in fully closed dies. These powder preforms of conrods for a high-performance sports car produce forgings which need little or no final machining, and they'll be lighter and stronger than conventional forgings. These commercial vehicle wheel nuts began life as atomized steel powder. To get really high strength, you need to use irregular-shaped particles. The powder is metered into a die cavity, and pressure is applied to produce a green preform. Separate particles cold weld together, and from the die set emerges a precise shape strong enough to be handled. At this stage, it's porous and very brittle. The preforms are then heated in a controlled temperature gas furnace. The first temperature, at 850 degrees centigrade, removes the wax or stearate, which was added as a lubricant at the first pressing. The second temperature, 1150 degrees, increases the interparticle bonding. But even at this stage, the component is still porous. A mixture of carbon monoxide and hydrogen provides carbon-containing gas, and this is carefully controlled so that carbon is incorporated into the preform. After the preform is removed from the sintering furnace, it can be cooled. Then it's loaded into an induction coil furnace, which has a protective carbon atmosphere of nitrogen and propane to ensure that the nuts don't surrender their essential carbon content. A single stroke of this 800-ton press completes the forging. This operation introduces a degree of grain flow into the metal and eliminates the porosity. The final product is therefore very similar in performance to a drop forging. It's been proved that the resistance to metal fatigue of powder-formed components is much higher than most other processes. But as always, there is a drawback. The powder itself is pretty expensive. Even so, powder forging is ideal for a whole range of components. The one great advantage of any form of forging is that in the process, the metal itself is enhanced. It becomes stronger and tougher.